Now that we are done with the discussion regarding the Big Bang Theory and its evidence, and on the previous video lesson that I've created, I already show you the glimpse of what our next topic is. Our topic for this video is about nucleosynthesis. Okay, so we are about to explore more on nucleosynthesis. This is the competency that we are about to reach after this presentation. Before we go deep dive into our main lesson, here are the things that we should remember. That atom is the smallest particle that makes up all matter. And atom is composed of proton, neutron, and electron. Proton and neutron are located at the nucleus of an atom, while the electron is located outside the nucleus of an atom. Sometimes, the term element is used as the other name of an atom. If we are familiar with the periodic table of elements, it shows the present elements that we know or known to the universe. Element is a pure substance that represents the species of an specific atom. There is also a term that we use in order to describe an atom. So that is the isotopes. So isotopes describes the atom of the same element but different atomic mass. So what does it mean? It only means that the same element but it differs in atomic mass, different in number of neutrons specifically. For example, mango is the specific atom, and mango has different kinds, isn't it? So the different kinds of the mango is what we call the atom. Mango are the elements and atom are the variety. Element is the identity and atom is the variety. The question is, how these elements are formed? After the expansion of the singularity, there is what we call the nucleosynthesis. It is the process which are about to create the particles. It occurred after the Big Bang. After split seconds, it started to form a proton and neutron. But before proton and neutron, there is what we call the quarks. So proton and neutron are made up of quarks. Nucleosynthesis is divided into three types, namely the Big Bang nucleosynthesis, stellar nucleosynthesis, and the supernova nucleosynthesis. When we look at the stars and the night sky, as well as our sun has stages, and that is what we call the life cycle of the star. So stars came from what we call stellar nebula. So this is the stellar nebula, and that stellar nebula is the combination of dust and clouds. So after the process, it will form into what we call protostar. So protostar is composed of particles where the stars came from. Stellar nebula, it's either will go on a life cycle of an average star or massive star. But we must talk first about the average star because as we know, Sun is an average star. From average star, it will go to a process of a red giant or cycle of red giant to planetary nebula into white dwarf. And then, the massive stars will go on a cycle of the red supergiant, supernova. It's either neutron star or black hole after the supernova. So there is a prediction that after 5 billion years, our sun will go on a life stage of a red giant. As we go on our lesson, we will discover what is the reason why average star or massive star turn into red giant and supergiant. And this is the reason why we are talking about the life cycle of the star is because of the activities happening in the star. So to produce a tremendous amount of energy, we must have a energy to live in a certain span of time. And the energy from the nuclear fusion between light elements to release energy to keep the star hot. What happened if the stars does not generate energy anymore? So as we go on, we are about to answer that question. So from nucleosynthesis, let's go on the first type of nucleosynthesis, which is the Big Bang nucleosynthesis. So as the universe cools, that is the time that particles can be fused to form elements. This is where the formation of light elements, and that elements are hydrogen and helium. And there is also an evidence that the other elements or light elements are formed in this type. So that is what we call the lithium. This is the illustration of the Big Bang nucleosynthesis. So from proton, so remember that this is what we call the hydrogen. Okay, so this proton is hydrogen combined with neutron. Okay, so this is the time that we call this one deuterium. So after the fuse of these particles, another neutron will fuse to the deuterium. So that is the time that we will call it tritium. Okay, as we go further, there is another proton of hydrogen or element or atom of hydrogen to fuse with the tritium. So that is the time that we are able to form, or that process we are able to form helium. So that is the Big Bang nucleosynthesis. So it's all about the formation of helium. Now that we are done with Big Bang nucleosynthesis, now let's go to the second type of nucleosynthesis, which is the stellar nucleosynthesis. So stellar nucleosynthesis is the process which elements are formed in the stars. So they are about to form hydrogen and helium, and there is what we call proton-proton chain. So it is the process where they are able to combine the 4 hydrogen into helium. The chemical reaction on this formation to form hydrogen is what we call the nuclear fusion. So proton-proton chain or proton-proton cycle is also called hydrogen burning. As I've said a while ago, that the fusion of 4 hydrogen is needed to form a nuclei or nuclei of helium. As you can see in this illustration, you can see that there is 4 hydrogen or 2 hydrogen on both sides, and after the fusion, the energy release and form another variety of hydrogen that releases gamma ray to produce another variety of helium. Okay, so there is helium there, and from that, helium-3 and helium-3 is fused together to form the what we call helium-4. Okay, so there is a 2 neutron and 2 proton. Okay, so that is why they call it helium-4. Aside from proton-proton chain or hydrogen burning, there is another process in order to produce helium, and that is what we call the carbon-nitrogen-oxygen cycle or Cno cycle. Cno cycle is the process of converting the hydrogen to helium among massive stars by using carbon as catalyst. So what does it mean? Always remember that Cno cycle occurs on the massive stars. They use carbon in order to produce helium. As you can see, carbon is the agent to provoke the nuclear fusion or nuclear activity in the stars. So in Tagalog, ginagamit nila yung carbon or yung carbon ang nagiging dahilan para makapag-produce ng helium. So as you can see in this illustration, this is where the Cno cycle starts. So from carbon, it will bombarded with another hydrogen that produces gamma ray in order to produce nitrogen. Since they are unstable, there is another chemical reaction that occurs, and that chemical reaction produces what we call positron, neutrino, and the carbon-13. So after that, another hydrogen bombard with carbon-13 to produce nitrogen-14. Okay, so don't forget that there is always radioactive particles released after the fusion of the particles. And let's continue. So another hydrogen bombard with nitrogen-14 to produce gamma ray and oxygen. And after that, another chemical reaction occurs, or nuclear reaction occurs, and then another positron and neutrino and nitrogen has been released or produced. So after that, nitrogen-15 is bombarded with another hydrogen in order to produce helium, and then back to carbon. So that is the Cno cycle. What will happen if hydrogen is being used up on its core? If proton-proton chain and Cno cycle stops, so what will happen? So that is the time that the helium starts to burn. So there is what we call hydrogen burning, and that is the time that another process will occur in order to produce another elements, and that leads to what we call the tri-alpha process. Always remember that alpha particles is equivalent to helium. So alpha is helium, which leads to the formation of beryllium. So as you can see in this illustration, as the two hydrogen or helium rather bombards together that produce gamma ray and beryllium, and beryllium and helium bombards together to produce gamma ray and carbon. In this illustration, you will see how the beryllium formed, and in the last process of tri-alpha process, it produces carbon, and that leads to what we call alpha ladder process. So when we say alpha ladder process, so it is a process of which reactions result to the formation of heavier elements up to iron. So as you can see in this illustration, this is now the carbon. Okay, so this is now the carbon. It will only add another helium in order to produce oxygen, and that oxygen add by another helium to produce neon, and so on and so forth. As you can see, as we add helium to the new formed elements, the higher the elements will produce. Okay, so that is what we call the alpha ladder process. It's just like a ladder of helium in order to produce another element up to iron. Now that we have learned how the elements are formed from hydrogen to iron, now the question is, how element heavier than iron forms? So it is believed that the reason why we have these heavier elements than iron, it is because of the supernova nucleosynthesis. So it is the pathway for heavier elements to be formed through the process of neutron capture. As you can see, compare to Big Bang nucleosynthesis and stellar nucleosynthesis, the supernova nucleosynthesis uses the process of neutron capture, not the nuclear fusion. So that is how differ the supernova nucleosynthesis from Big Bang nucleosynthesis and stellar nucleosynthesis. Neutron capture, in order for to create a heavier elements, it is also create. Now, neutron capture also create heavier isotope of the same element in order for it to become stable or radioactive. So when we say radioactive, it is, or these are the unstable nuclei. Example of this are the beta decay. As you can see, as the neutron is captured, it will automatically added to the nucleus or the seed nucleus. So there are two types of neutron capture, and these are S process and the R process. S process from the word or from the letter S, which means slow, and from the letter R, which means rapid. So as you can see the difference between these two. So when we say slow process neutron capture is where the addition of neutron occurs after the release of the beta decay. Okay, while the rapid process, it adds or it captures neutron before the beta decay release. So that is the difference between these two. As you can see in this illustration, how neutrons bombards with the original element nucleus. Okay, so and how the unstable neutron heavier than or heavy element nucleus release beta decay. Okay, so in order to produce new element. In summary, we have learned that the nucleosynthesis is the process in order to create elements. Okay, so there are three types of nucleosynthesis, and these are the Big Bang nucleosynthesis, stellar nucleosynthesis, supernova nucleosynthesis. And Big Bang nucleosynthesis is the formation of light elements, while the stellar nucleosynthesis is the formation of hydrogen to iron. Okay, so from the process of proton-proton to CNO to tri-alpha process up to alpha ladder process. So now, compared to this one, or compared to this Big Bang nucleosynthesis and stellar nucleosynthesis, supernova nucleosynthesis is used neutron capture in order to produce heavier elements, and these are divided into two processes, and these are the S process and R process. And we also learn about the life cycle of the stars.